Generalized synthetic division, a demonstration. Before synthetic division begins, I suggest writing the rational expression with the following rules. Powers in the numerator and denominator are in descending order. Write all terms in the numerator and denominator polynomials. Any power not appearing in the original rational expression has a 0 as its coefficient. The leading coefficient in the denominator is 1. And finally, the terms in the denominator are all subtracted. Our first example will have a linear divisor, and we're asked to find the quotient and remainder for the following rational expression: 2x cubed plus 3x squared plus 4 divided by x plus 1. Our first step is to write it in our expanded form. So we have 2x cubed plus 3x squared plus 0x plus 4 divided by 1x minus negative 1. Now this is our expanded form, and it has a few things that I want to note. First, we do have a 0 coefficient. Our original rational expression skipped the x term, so we add that back in with a 0 coefficient. Our leading term in the denominator has a coefficient of 1, and our terms in the denominator are being subtracted. So when you have an x plus 1 in the denominator, like shown here, we're going to change that to x minus negative 1. With these changes, we are now ready to build the synthetic division table. Now that we have our expanded form, we're ready to build our table. And here I have constructed a table where you have the powers on the variable displayed as the column headings for our table, and these things correspond to the powers on the variable in the numerator. We have a black horizontal line drawn here to separate the coefficients for the remainder and the quotient from our table work. We have a red vertical line drawn here as well to separate the numbers that go with the quotient and the numbers that will go with the remainder. And finally, I put a indication that we're going to add the numbers that appear in the columns after we put them in there. So this is basically how our table is going to be set up, and this is also how generalized synthetic division is essentially set up. So we'll go ahead and move these coefficients from the numerator into their respective columns. We'll go ahead and move that negative 1 from the denominator into its respective cell, and this corresponds again to the constant from the denominator. Now we have all of the numbers that we need in order to perform synthetic division. Since our leading coefficient in the denominator is 1, we can bring the number 2 straight down. So the coefficient of x cubed in our example just gets copied straight down. Our next step is to multiply the negative 1 and the 2 together, and we're going to put that result in the cell where the green arrow points. So we'll go ahead and do that. And of course, negative 1 times 2 is negative 2. And now, as indicated on the far right, we will add these two numbers together. So 3 plus negative 2 is 1. We will repeat this process with this new value. So we'll go ahead and multiply negative 1 times 1, and we will put the result in the cell where the green arrow is pointing. And of course, negative 1 times 1 is negative 1. As our indication arrow shows on the far right, we will add these two numbers together. So we'll go ahead and add 0 and negative 1, and we get negative 1. Now we've reached the red line in our table. This indicates that we are completed with finding the numbers for our quotient, but we still got to find the number for the remainder as the question asked. So we'll go ahead and multiply negative 1 times negative 1 one more time. We'll put the result in the cell where the green arrow is pointing, and we will go ahead and add the 4 and the 1 together, and we get 5. And this 5 corresponds to our remainder. So we are now ready to form the quotient and the remainder from this division. Now, because we divided x cubed by x, we drop all the powers on the variables down by 1, and those are all the columns that are to the left of the red vertical line that I've drawn. So our quotient will have a 2 multiplying x squared, a 1 multiplying an x, and a negative 1 as a constant. And again, I've reached the red line, which means the terms beyond this red line form the remainder. So we have 5 as our remainder. So according to the division algorithm, we have the rational expression 2x cubed plus 3x squared plus 4 divided by x plus 1 can be written as 2x squared plus 1x plus negative 1 as the quotient polynomial plus 5 over x plus 1. Now the 5 corresponds to the remainder. The 2x squared plus 1x plus negative 1 corresponds to the quotient, and the numbers that are written in red here correspond to the exact same numbers we got when we performed the synthetic division. Our second example deals with a quadratic divisor, and we will find the quotient and remainder for the following rational expression: 8x to the fourth minus 4x cubed plus 12x squared minus 10x plus 2, all of that divided by 2x squared minus 6x plus 4. And first we're going to write this in our expanded form. Now let's review our rules here. First rule of the expanded form is that all of the powers in the numerator and denominator are descending, and that happens to be the case here, so there's no need to rearrange terms to make that happen. Our second rule states that if any power in the numerator or denominator is skipped, we have to write that back in with a 0 coefficient. Now fortunately, that does not occur here either. All of the powers on x are accounted for in the numerator and in the denominator. Our third rule says that our leading coefficient in the denominator has to be 1, and that rule is violated here. Our leading coefficient right now is 2. So we need to factor out the 2 from the denominator. All the terms in the denominator have to be divided by 2 in order to factor it out. So we've done that here toward the bottom of the screen. We have a 2 factored out of the denominator. And what we're going to do is we're going to divide this 2 into each one of these coefficients in the numerator. This will effectively accomplish what we want to do when we come to our synthetic division table. So we've gone on ahead and done this, and that is where our numerator coefficients come from. The last rule that we have to remember is that all of the terms in the denominator are subtracted, and that means all of the pluses become double negatives, if you will. So our rational expression that we're going to apply synthetic division to comes to 4x to the fourth minus 2x cubed plus 6x squared minus 5x plus 1, all of that divided by 1x squared minus 3x minus negative 2. Now we have satisfied the 4 rules, and now we are ready to build our synthetic division table. Now that we have our expanded form, we can go ahead and build our table. And as shown here, we have our columns corresponding to the powers on x from the numerator. We have a black horizontal line to separate the work from the results. We have a red vertical line to separate the quotient numbers from the remainder numbers. So we'll go ahead and copy the coefficients from the numerator under their respective powers of x. So 4 will go under the x to the fourth column, negative 2 will go under x cubed, and so on. our denominator terms will also be copied over to their respective cells. And here we have the x coefficient from the denominator at the bottom of our column that we've copied these over, and we have the constant from the denominator in the cell above that. And this is done to make the construction of the table easier to follow and easier to build. So let's go ahead and begin with the synthetic division process. Our leading coefficient in the denominator is 1, and that means that we can merely copy the leading coefficient from the numerator below the black line, in this case 4. Now we'll go ahead and multiply the 3 times the 4, and we'll put the result where the green arrow indicates, and 3 times 4 is 12. We will go ahead and add the -2 and the 12 together, because they're in the same column, and we get 10. Our next step is to multiply the 3 and the 10 together and put the result where the green arrow indicates. And 3 times 10 is 30. After we do that, we will take the -2 times the 4, and we will put the result where the yellow arrow indicates. And -2 times 4 is -8. Now we will add the numbers in the x squared column together. That is 6, -8, and 30. We will add all of those together, and when we do, we get a result of 28. Now that we've reached the red line in our table, we have found all of the coefficients that belong to the quotient. We still need to find the numbers that correspond to the remainder. So again, we'll repeat our process. We'll multiply 3 and 28 and put the result where the green arrow indicates, and 3 times 28 is 84. We will then multiply -2 times 10, and we will put the result where the yellow arrow indicates, and -2 times 10 is -20. We will add these numbers together that are in the x column, the -5 plus -20 plus 84, and when you do that, you get 59. Our final step in building the synthetic division table is to multiply the -2 times the 28 and put the result where the yellow arrow indicates, and -2 times 28 is -56. And now we may add these numbers together, 1 plus -56, and we get -55. Now that we have found all the coefficients for our remainder, we may now construct the quotient and the remainder to answer the question. Because we divided x to the 4th by x squared, all of the powers on the left side of the red line will drop by 2. So the x to the 4th that we had originally, that's going to drop to x squared for the quotient, and that means that our quotient begins with 4x squared. The x cubed column will drop to x, and that means that our quotient has a 10x in its result, and the x squared will drop to a constant, meaning that 28 corresponds to the constant for the quotient. Now that we've crossed over the red line, the powers do not drop at all. So the 59 that appears in the column for x, that's going to be the x coefficient for the remainder, and the -55 in the constant column will also correspond to the constant term for the remainder. Now, because the leading coefficient in the denominator was not 1 initially, the values in the remainder part of the table are incorrect. This table and this needs to be adjusted as follows. Right now we have 59x minus 55 divided by x squared minus 3x plus 2. But remember, way back at the beginning, we factored out that 2 so that we could do the synthetic division. Now we need to put that back in. So we multiply the bottom by 2 in order to get back to our original denominator, but we can't just multiply the bottom by 2, we've also got to multiply the top by 2. And when we do that, we get 118x minus 110 divided by 2x squared minus 6x plus 4. So just a simple note is that if it was factored out at the beginning, it needs to be multiplied back in after the synthetic division process is complete. And another part, this only is done in the remainder. It is not done to the quotient, only in the remainder. So the original denominator must be present in the remainder before you make any reports about what the quotient and remainder are. So according to the division algorithm, we may rewrite the rational expression as follows. We have our original expression, 8x to the fourth minus 4x cubed plus 12x squared minus 10x plus 2 divided by 2x squared minus 6x plus 4 may be written as 4x squared plus 10x plus 28, that's the quotient, plus 118x plus negative 110, that part is the remainder, divided by 2x squared minus 6x plus 4 again. So when reporting the remainder, the original denominator must be used to ensure its accuracy. You cannot go directly from the table. And this occurs if you have to factor a number out from the denominator to make that leading coefficient equal to 1. Our third example has a cubic divisor. And we will again find the quotient and remainder for this expression. X to the sixth plus 3x to the fourth minus x squared plus 7 divided by x cubed plus 2x squared minus 3. And again, we're going to apply the rules so we can write it in our expanded form. Powers in the numerator and denominator are decreasing, so there's no need to rearrange terms. We've skipped some powers in both the numerator and the denominator, so we have to put in 0 coefficients where those powers were skipped, and that is shown here. The leading coefficient in the denominator must be 1, that is already done, and the terms in the denominator must all be subtracted. So any pluses again have to change to a double negative, and we have that accomplished here as well. So when we write this rational expression in our expanded form, we have this: x to the sixth plus 0x to the fifth plus 3x to the fourth plus 0x cubed plus negative 1x squared plus 0x plus 7, all of that divided by 1x cubed minus negative 2x squared minus 0x minus 3. We have now fit the form to build our synthetic division table. Now that we have our expanded form, we can go ahead and build our table. And our table has the column headings that correspond to the powers on the variable x from the numerator. So we'll go ahead and copy those coefficients down so that they are underneath their respective powers of x. And we will also copy over the coefficients from the denominator. And again, we will stack them up so that the powers on x decrease as you move up. And again, this is a preference to make the table easier to construct and apply. So the coefficient of x squared from the denominator is at the bottom of this column. The coefficient of x from the denominator is in the cell above that, and the constant term from the denominator is in the cell above the coefficient of x. Now we're ready to begin our synthetic division. The leading coefficient in the denominator is 1, so I may merely copy down the leading coefficient of the numerator, in this case 1 as well. Now we will begin multiplying. Negative 2 times 1, the result of that goes where the green arrow points in that cell, and that is negative 2. We then add all of the numbers in the x to the fifth column. That's 0 plus negative 2 and that result is -2. We now multiply -2 times -2, and we get a result of 4. We put that in the cell where the green arrow is pointing. And then we take the 0, the coefficient of x from the denominator, that's 0, and we multiply that by 1, and we put that in the cell where the yellow arrow is pointing. And 0 times 1, of course, is 0. We now add all of the numbers in the x to the 4th column, and that's 3 plus 0 plus 4, and that becomes 7. Repeating the process again, -2 times 7, the result goes where the green arrow points, and that's -14. 0 times -2, the result goes where the yellow arrow points, and that is 0. 3 times 1, and that result goes where the purple arrow points, and that is 3. Then we add all of the numbers in the x cubed column, and that is 0 plus 3 plus 0 plus -14, and that becomes -11. We have reached the red line. That means all of the coefficients of the quotient have been determined. We still have to determine the coefficients in the remainder though. So we'll continue this process. -2 times -11, and the result goes where the green arrow points, and that's 22. 0 times 7, the result goes where the yellow arrow points, and that is 0. 3 times -2, and the result goes where the purple arrow points, and that is -6. We then add all of the numbers that are in the x squared column. That is -1 plus -6 plus 0 plus 22, and that is 15. Continuing our multiplication process, except this time we start with the 0, the coefficient of x from the denominator. And we take 0 times -11, and we put the result where the yellow arrow points, and that of course is 0. And then we take 3 times 7, and we put the result where the purple arrow points, and that is 21. And then we add the numbers in the x column, 0 plus 21 plus 0, and that of course is just 21. We have one more multiplication to complete, and that again starts with the constant from the denominator this time. 3 times -11, and we put the result where the purple arrow indicates, and that is -33. And then we add the numbers in the constant column, and that's 7 plus -33, and that is -26. Because we divided an x to the 6th polynomial by an x cubed polynomial, all of the powers in the quotient are going to drop by 3. So the x to the 6th column, that we have our 1 as the leading coefficient for the quotient, that's going to be the leading coefficient of the x cubed term. The x to the 5th, which gave us the -2 number for the quotient, will be the coefficient of x squared in the quotient. The 7 will be the coefficient of x, and the -11 will be the constant term in the quotient. Now remember, once you cross over the red line into the remainder, you do not drop the powers. So the column headings in our table will also correspond to the powers on x for the remainder. So the 15 that we see here is the x squared coefficient for the remainder. The 21 is the x coefficient for the remainder, and the -26 is the constant term for the remainder. And now our synthetic division table is built. So the quotient and the remainder for the rational expression are as follows. We have 1x cubed plus -2x squared plus 7x plus -11 as the quotient, and then we have 15x squared plus 21x plus -26 as the remainder. You try. Using generalized synthetic division, find the quotient and remainder for the following rational expression. 2x to the 7th minus 3x to the 6th plus 5x to the 3rd minus 4x to the 2nd plus 1, all of that divided by x to the 3rd minus 3x to the 2nd plus 2x minus 4. And I recommend you pause the video here to give you time to try to build the table. The next slide has the table resulting from generalized synthetic division. Here is the synthetic division table that should be generated from the previous example. I hope you got this one. According to the division algorithm, the rational expression may be rewritten as follows. Here we have 2x to the 4th plus 3x cubed plus 5x squared plus 17x plus 53 as the quotient. And then we have 156x squared minus 48x plus 233 as the remainder. And of course the remainder is always going to be divided by that denominator from the original expression. Try a quartic divisor. Using generalized synthetic division, find the quotient and remainder for the following rational expression. And as a hint, don't forget the form. You may want to pause the video here because the next slide has the synthetic division table generated when you apply the process to this rational expression. Here is the synthetic division table for the previous example. I hope you got this one. From our synthetic division table, and according to the division algorithm, our rational expression may be rewritten as follows. 1x cubed minus 4x squared minus 3x minus 13 plus 51x cubed minus 243x squared plus 75x plus 204, and that is divided by the original denominator, 3x to the 4th plus 6x cubed minus 12x squared plus 18. Do not forget about adjusting that remainder term. Here is the research paper where generalized synthetic division is established and several results are proven. Thank you for your time and attention, and good luck to you in applying generalized synthetic division.